Ok, très bien.
So, dear Frédéric, thank you for giving the talk to this seminar, and that's a real pleasure to hear of someone working with the same tools as we wish to use in this project. And so, thank you for explaining us what you are doing now. Okay.
Thank you, Paul. So if we are enough, I will start. So today I would like to talk about how to infer interaction between species using Granger causality and convergent cross-mapping. And this is some work that I've been doing at the Institute of Mathematics of Bordeaux. I'm a researcher at the CNRS. And I would like to say also that I'm a quantitative ecologist. So I'm not a mathematician. I'm a biologist within a mathematics lab, but by training, I know a little bit of mathematics, but I'm not really a mathematician. And I've been doing this with Coralie Picoche as well, who works with me as a PhD student, and Matteo Detto, who's in the US at Princeton, and Florian Artigue, who's doing quantitative ecology as well at the University of Regensburg in Germany. In ecology, quite often, we want to reconstruct interaction networks. And interactions is a term that can have many meanings. So we need to define it a little bit. And for the remainder of this talk, I will consider that there's an interaction in a dynamic sense if when I change the population density of one species, the population growth rate of the other species changes as well. So for instance, if lynx population size fluctuates, then it will make the coyote's population growth rate, the derivative, fluctuate in this small network. Now, this type of relationship is something that we can try to infer from time series data. So let's say we have time series like the ones on the right, where you have a prey in blue, Paramecium, and a predator in red, Didinium. As you can see, the red time series is slightly shifted to the right. And the reason for this is that the prey fluctuations are causing the predator fluctuations, and the cause slightly precedes the effect. In that particular case, as we will perhaps see later, there's probably a reciprocal effect. So the predator also causes fluctuation in the prey. But what we see mostly in the picture is the cause preceding the effect. And as you may already know, a key notion of causality is basically a more formal way of saying that the cause precedes the effect. So if we think about Granger causality, we would say that X Granger causes time series Y if when we include X in a time series model for Y, it improves the prediction of Y, or future values of Y. And the way we do this in practice, which is a little bit different from the general definition, is to make a time series model, usually a linear one, without time series X, a time series model for Y with time series X. And then we say there's pairwise Granger causality if the residual variance decreases. And then we can compute things like effect sizes by using the logarithm of the ratio of the variances. And this is something that has been done a lot in econometrics, in neuroscience. In neuroscience, they have a lot of generalization of this concept using different nonlinear techniques, transfer entropies, and so forth. It has been done in genetics as well, and a little bit in ecology by one of my co-authors. So I think the people listening today will know, of course, this already. I'm just stating it so that we can move on to new things. In ecology, what has been quite popular in recent years is a technique called convergent cross-mapping. So it's been developed by George Sugihara and co-authors, and they put forward this method in a paper called Detecting Causality in Complex Ecosystem, which has been published in Science and has had a quite large impact. So in this paper, they suggest that although Granger causality is an improvement on correlations using correlation, which, as we all know, is fairly bad if you have a time series with autocorrelation, um, it still has some trouble dealing with a system in which there's a high degree of entanglement. So I say entanglement for lack of a better word. Um, and the kind of dynamical systems they have in mind are chaotic system with a strong degree of coupling between each component, like the Lorentz attractor. In the Lorentz attractor, for instance, there's information about the free state variable in any of those state variables. So the idea is that we cannot do the same sort of partitioning that we do with Granger causality when there's the strong degree of nonlinear coupling within a dynamical system. At least that's what they put forward in the paper, and they call these separability issues, and I put the separability within quotes because it's not very well defined what they mean exactly by separability. And as you know, the mathematicians may know, this word has many different meanings in many different contexts. So there are other methods of state space reconstruction than the one used in convergent cross-mapping, but there's, we have only one flavor of these kind of techniques in the ecological literature. So how does that work exactly? So you have the Lorentz attractor on the top left, where you have the free state variables x, y, and z, and they uh, call the attractor M with an M for manifold, showing the shape of that structure. And you can reconstruct, due to Taken's theorem, reconstructed attractors mx and my using delayed coordinates of any of those state variables. So you can use delayed coordinate of x, delayed coordinate of y to reconstruct the same shape of the attractor. And then what they've showed, which is quite interesting, is that if variable x causes variable y, in the sense that the population growth rate of the derivative over time of y is affected by changes in state variable x, it means you can predict xt value from my, from this reconstructed attractor. The way you do this in practice is by looking at the correlation coefficient. So you compute the correlation coefficient between the values of x and the values of x predicted given the knowledge of this manifold y. You can see an example on the top right panel where I plot the time series of paramecium and didinium. You have the prey in blue and the predator in red again. And on the very top right, you can see values of the correlation coefficient using different quantities of data about variable about this my. So L here is the amount of points on my that you use for the reconstruction, and it's called convergent cross-mapping because as you increase the number of points, you should see a convergence of this correlation coefficient. So in that case, because the correlation coefficients are both high, both high, we conclude that paramecium causes didinium to fluctuate and didinium causes paramecium to fluctuate. But there's something which is a bit puzzling. It's what they call causality reversion. So with convergent cross mapping, if X is causes Y, it means you can predict the cause X from this reconstructed attractor with variable Y. And this seems to oppose the classical notion of Granger causality, because in Granger causality, if X is causes Y, it means that by using X values to predict Y, you do better than only using Y values. So it looks a bit from these two definitions, superficially at least, like those two techniques might be very different. Of course, I'm sure that most of you may think that, well, the definitions are not exactly the same. In one case, we predict the future. In the other case, we don't. And that partly that will explain why, these methods are perhaps less different than one might think. But superficially, they look very different because it looks like the sense of prediction is reversed. Now, the critique of Sugihara and co-authors was likely directed at applying Granger causality for something else than a linear stochastic system, but they didn't really say what they meant by linear stochastic system. So I'm going to make this more precise. By linear stochastic system, they meant the classical models that Granger was using and that many people have used in econometrics after that. And these are multivariate autoregressive model, or as we say in econometrics, vector autoregressive models. For some reason in ecology, people use multivariate autoregressive model. I don't know exactly why, but I mean the exact same thing. So what we do is that we consider population size or population densities, which I denote NT, and then we take the logarithms of these quantities, and then we write this equation 3, where you relate xt to xt plus 1 to xt with an interaction matrix B. And you might want to add some control variables or some external forcing, UT, that act as a forcing term. And this has been done quite a lot in ecology. So there's a famous paper by Tony Ives and co-authors. They have all the theory in there. They have an example on zooplankton, and many people have used this type of models, including me. And the coefficients in this interaction matrix are in fact conditional Granger causality coefficients, because the effect of the coefficient Bij here, if it's non-zero, represents the causal effect of species J on species I, given all other variables. So ecologists have used this Granger causality concept, in fact, unknowingly, and quite repeatedly over the last 2 decades. And many people often ask why the logarithmic transformation, and that's a good question. So the first answer is that population size are often log normally distributed. So the logarithmic transformation gets it back to the normal scale, the Gaussian scale. The other reason is that most population growth processes are multiplicative. So the logarithmic transformation allows you to, make better use of the additive relations in the multivariate autoregressive model. And when people are still, skeptical, I usually show them the untransformed, the back transformed um, formulation, which is at the bottom right, which is essentially a power law model. So I illustrate here for three species, and as we all know, power laws are a quite flexible way to represent nonlinearities. Of course, power laws are monotonic, so you can't represent everything, but it's still uh, useful representation. So the logarithmic transformation is an important thing here. The reasons why linear Granger causality might in fact apply to highly non-linear ecological system is, as I said, that it's in fact a power law model, and we've shown that even the simplest multivariate autoregressive model with one time lag, in fact, are quite robust to slight change in the assumption. So we've considered more nonlinear model with saturating interactions and things like that. And we managed to recover the right signs of coefficients about 80 to 95% of the time in a previous study. So they work quite well. And in general, we, of course, test for Granger causality using more time lags. So we would do a model selection that will select the lag order of this multivariate autoregressive model of order P. And as I'm sure many of you already know, you can have a large increase in the flexibility of the model, even for a small increase in the number of time lags. And a good example of this is given by the autoregressive, the single population autoregressive model. If you have an AR1 model, you cannot have cycles of any periodicity. But with an AR2 model with only two time lags, you can basically have cycles of any periodicity and a variable amplitude as well. So of course, an AR2 model won't be able to mimic all sorts of oscillations. There will be oscillations that are not well captured, but still, it will give you an approximation. So given all this, given the high likelihood that in fact linear Granger causality is quite robust to deviations in the functional form of the underlying data generating model, we re-evaluated the relative performance of Granger causality and convergent cross mapping by using a number of time series ranging from highly nonlinear in the sense of close to deterministic chaos, positive Lyapunov exponents, to linear in the sense of multivariate autoregressive models. So we've used a set of data and models to test these techniques that was partially overlapping with Sugihara and Kurota's choices. So we use this predatory data from Veilleux, which I showed you before, that are believed to almost like a limit cycle. And then we used the chaotic and deterministic two-species logistic competition model, also in the original Sugihara paper. And we considered this model with interaction between the species, these terms here, and we considered also the model without interaction between the species. We do this for all models to test for the possibility of false positives. Now we have used we have crafted models of our own, these Ricker-based competition models. So the previous model I showed you, it's a little bit ill-behaved. It can have negative densities. And so we have put the Lotka-Volterra interaction term within an exponential here. It's called a Ricker model in population ecology. And this model is still a chaotic model, can still generate chaos, but it's better behaved. And what we did as well is to add some sort of stochasticity, this epsilon1 and epsilon2. And then we did the same thing as before. We simulate the model with the interaction between the species, and we simulate the model without interaction between species, with interaction only within species. And because it wasn't hard enough, we decided to do something a little more tricky. So we considered a strongly autocorrelated covariate that forces both populations to go up and down at the same time. So this is the green forcing term here, which you have plotted over time. And as you can see, there are long period cycles, a strong autocorrelation. And this is supposed to make life hard for any inferential method. As you will see, it succeeds quite well in doing that. Then we also wanted to have cases with higher dimensionality. So here we have, again, a Ricoeur-based Lotka-Volterra style of models, where you have an interaction matrix A here, which I represent at the bottom. We have chosen to have a modular interaction matrix because many ecological networks are modular. And as you can see, the third module is independent from the rest, but the first two modules are connected. So we have some connecting species, and it will be interesting to see if when estimating causality, we can get back both the modules and the species connecting the modules that have probably an important role in the ecosystem. I mean, in our theoretical ecosystem, at least. This particular parametrization that we use, both for the interaction matrix A and the population growth rate, maximum population growth rate R, is so that you have a positive stochastic Lyapunov exponent. So there is noise as well, quite a bit of it, but there's a strong divergence of trajectories, which is reflected by the positive stochastic Lyapunov exponent. So uh, I think that there are a few mathematicians who follow this, so you probably know what are stochastic Lyapunov exponent, but otherwise I'm happy to answer later on. Now, we wanted to differentiate the effects of how strong are the interactions between the species from how nonlinear the model is. So we made a linear approximation uh, or power law approximation on the n-transform scale of these Lotka-Volterra models. So to do this, we get back to the log scale, then we compute the Jacobian, and as it turns out, with the particular formulation I showed you before, the Jacobian has a very simple form, and it's Kronecker delta plus coefficient multiplied by the densities at equilibrium. So after that, we decided to complexify this again and go for a 20 species model. So with a 20 by 20 interaction matrix. And as you can see, there are plenty of zeros. So we will have a lot of opportunity to monitor false positives. In this particular case, we decided to have variable interaction strength. So for each simulation run, there is some variability in the non-zero interaction strength. All right, so now I've described to you all the models. Perhaps I can take some questions on the models if there's something that you don't follow. No questions?
I have just one question. I wonder if those models don't look like those introduced by our friends from Chile. That means Rebolledo and Pablo Marquet and people like and others, which are making very close models, in fact, but they are not. They are less linear, I think. Did you hear about them?
So one thing I should precise is that there are two meanings to the term nonlinear. You can say nonlinear to say that you're close or far away from chaos. And so this is a relatively objective nonlinearity concept because you can measure it with a Lyapunov exponent. Then there's also whether the interaction strength are strongly saturating. And you can have strongly saturating interaction strength without having a positive Lyapunov exponent. And conversely, you can have a positive Lyapunov exponent without having saturating interaction strength. So as far as I know, the models developed by Pablo Marquet and co-authors, and perhaps Sonia Kefi, they have interaction modifiers. So there's more than two species involved in an interaction. I think that's how they do it. So the functional forms somehow saturate with more species, which is one meaning of the term nonlinearity. But here, when I say nonlinearity, because the Shugihara paper associated nonlinearity to chaos theory, I mean that the systems are close or far away from chaos. I hope that clarifies things.
Okay, thank you. Sorry. Thank you.
Good. So now to the statistics. So then we had to evaluate causality on these models. So for the two species models, we did these pairwise Granger causality tests, and we used the alpha level of 10%, and we also used an effect size threshold. So you're probably thinking like, why an effect size threshold? So imagine you're under the null hypothesis, and there's no interaction between the two species. Normally, you would think that, in that case, p-values are uniformly distributed between 0 and 1. However, that's only true if the model that generates the data and the model that you fit to the data are exactly the same. Otherwise, that's not exactly true, and you can have some artifactual small effects. So to thin out the artifactual small effects, we used an effect size threshold. For the selection of the number of time lags in the vector autoregressive model, we used classically BIC. And for the tests themselves, we used val test for coefficients in the R package LM test. And we also used for conditional Granger causality F tests. And we compared these F tests to the val test, and they almost always say the same thing. For convergent cross mapping, we also use the same alpha levels, of course, and we produce p-values, and we use an effect size threshold. And the p-values are surrogate based. So again, I suspect that many people know what surrogate time series are, but for those who might not, surrogate time series are if you have a vector of time series and you want all your component time series to be independent, you can do transformations on your time series that will erase the correlation between the component time series. So the easiest way to do this is to do a permutation on your values along the time series, but it destroys the autocorrelation. So in that case, we did permutation based because when we compare to more sophisticated method, it didn't change anything, at least for the case where we have checked. But there are more sophisticated methods that allow you to keep the same Fourier spectrum, for instance, but erase the cross correlation between time series. And we've done this in the package REDM, which implements this convergent cross mapping. Now, for the many species models, of course, if we do pairwise analysis, we make many comparisons. So we consider the Benjamini and Hochberg correction to control the false discovery rate. And we also tried conditional Granger causality. So for this, you have to fit a full-scale multivariate autoregressive model. And for this, we used a technique developed by Camille Charbonnier, Julien Chiquet, and co-authors, which is called SIMON for Statistical Inference for Modular Networks. And it's a weighted lasso approach. So it combines element of group lasso, in which you set blocks of parameters to 0 simultaneously, and adaptive lasso, in which the weights for the lasso are in which there are weight in front of the penalties for the lasso. So this is a quite elaborate technique, and I must admit that I have a limited mastery of it. So for details, I would refer to you to the nice paper by Camille Charbonnier and co-authors. But just to give you some idea, there's a latent structure of the network, which has a number of classes, and you have an indicator function which tells you like which species is in which class. In their case, they were looking at interaction between genes, so they look at which gene was in which class. And then you have a loss function with a penalty term in equation 18, where you can see that the penalties, they are encapsulating this network structure. So there is a latent network model which tells you if two species will be connected. I call them species, but in their case, it's much more general. It could be anything, really. So this is the philosophy of the statistics. And, you know, as important as the theory is the practice. How do you find those coefficients? And they have found an algorithm which is quite efficient, and they managed to reduce this global lasso optimization to a number of D lasso style problems, and that makes it much faster. And then they tune their penalties using BIC, and there's much more details in this nice paper. So now I will leave the weighted lasso and move on to the results. So I go back now to two species models and pairwise Granger causality testing. So on the right panels, you see the sensitivity and specificity for our two species models. So I have deterministic chaos, two species competition, stochastic two species competition, and two species competition and a driver, which means forcing by this green temperature variable. And we will first look at deterministic chaos. So I have the results for Granger causality in blue, and the results for convergent cross mapping in gray and black. So for the sensitivity, what you see here is that quite surprisingly, Granger causality and convergent cross mapping give almost identical results. So the big dots and diamond here, they represent both interactions. The dark symbols on the top, they're for the strong interaction, and the light symbol here, they are for the weak interaction. So in all cases, you see that the Granger causality and convergent cross mapping say the same thing. For the weak interaction or the strong interaction, they say the same thing, and they have the same performance on average in terms of sensitivity. And in terms of specificity, Granger causality works a little better than convergent cross mapping, but it's overall the same thing. So this is quite surprising, because in this case, we expected convergent cross mapping to work perfectly and Granger causality to not work at all, because it wasn't developed for that. And then for the two species stochastic competition, we see again that the performance is very similar, and both methods work really well. And then when we add a strongly autocorrelated forcing to the dynamics, you have here more difficulty with Granger causality, in that the strong interaction on the top is picked up correctly, but the weak interaction at the bottom is not. So just perhaps to clarify, but in our two species systems, there's always let's say, interaction from species 1 to species 2, which is stronger than from species 2 to species 1. So that's why I'm talking about the weak and the strong interaction. So conversion cross mapping had high sensitivity there, but it also had a worse sensitivity. So both methods here failed to some degree. When we go to the many species cases, as you can see in blue, you have the performance of Granger Cautality, which is overall fine, both in terms of sensitivity and in terms of specificity. You expect that the sensitivity won't be perfect with such large networks. So conversion cross-mapping doesn't work so great for 20 species systems for reasons that we haven't figured out exactly. But overall, otherwise, both techniques are, saying more or less the same thing. So here are the same results, but presented slightly differently. So previously, I showed you the results of this pairwise testing with Granger Cautality. So we test for, if we have 10 species, there's 90 possible combination, and then we do a Benjamin-Yoshper correction to avoid a crazy increase of the false discovery rate. And in that case, it works remarkably well, as I showed you before. And we can compare this to the predictions of Simon. So this is the lasso-based penalized multivariate autoregressive model, which works very fine in some cases, especially when the true model is the model that we fit, the multivariate autoregressive model. But when the model that we simulate is the Lotka-Verdura model, in gray here, it works a little less well. Regarding the conversion cross-mapping, we see that it works well for 10 species, but for some reason not well for 20 species. And on the bottom left panel, we consider the other kinds of p-values. And I won't dwell much on that, but the bottom line is that your choice of p-value is really important. Now, let's look at the interaction networks that we estimated. So as you can see, we get back the 3 modules that we saw before. So if you have a large green circle, it means very green circle. It means that you recover well the interaction. If you have a large square, it means that there is a lot of false positives. And we also recover the connecting species between those 2 modules, which is fairly nice. So conversion cross-mapping works well, although slightly less well. Now, if I compare to the lasso estimates of interaction, you can see here that there is a little more false positives, probably because in that case, the Lotka-Verdura model that we simulate isn't exactly the model that we fit, and the lasso-based approach is a little more sensitive to that. Now we go to 20 species when this worked really fine. And we recover also like both the modules and the species connecting the modules, which is fairly nice. And at the bottom, you have a case where we have used the conversion cross-mapping, which doesn't work great in that particular case. And on top here, you have the results for the lasso-based multivariate autoregressive technique. And for the 20 species case, which was a little less nonlinear, like with negative Lyapunov exponents, it worked quite well. So here are the results, and I will go back now for the conclusion to two-species systems. So in most of our two-species case of fluctuating community dynamics, both techniques were surprisingly, although they may look different, they gave the same answers. And it was difficult to understand how Sugihara and co-authors managed to say that Granger causality was not working in the case that they considered, because we used the same data and models. So the most likely is that they used a different model selection. So we used BIC, and in some cases they had over-parameterized models with very long number of maximum tag lags, because they use a sequence of likelihood ratio tests to do their model selection, which is, as you may know, is not really what is recommended. In some other instances, I don't exactly know how they managed to not find the interaction with this convergent cross-mapping. There's one notable exception, is when you have nonlinear competition, strongly nonlinear competition, with a strongly autocorrelated abiotic driver, which is forcing the dynamics of both species. In that case, the Granger causality is producing false negatives, and the convergent cross mapping false positives. And we've done additional analysis that haven't presented here, and we can show that both strong nonlinearity and an strongly autocorrelated environment are completely fine taken on their own, but when you combine them, it creates problems. And it's not so surprising, actually, because we know that even if you look at single species population dynamics, if you have a strong autocorrelation in the forcing by, say, temperature, and you have a sort of chaotic dynamics, a boom-bust cycle or something like that, then it's known that it's quite challenging to estimate these two parameters separately. So we could have expected, this difficulty. But the bottom line is that there's nothing wrong with using Granger causality for limit cycles and chaotic attractors. By contrast to what one may have thought reading this Sugihara paper. And there's nothing wrong as well with using convergent cross-mapping for relatively stochastic dynamical systems, even though it wasn't really developed to do that. And me and my co-authors, we think that probably both methods agree, because they define interactions in the same way. In both cases, we have the derivative of the state variable, the population growth rate, which is a function of population densities. So the definition of what is an interaction in the model is the same in both cases. Now, going to many species, 10 by 10 or 20 by 20 interaction matrices, surprisingly, the pairwise Granger causality with a Benjamini-Hochberg correction was really efficient. I didn't really expect that. Doing the same correction with convergent cross-mapping wasn't so great, but on the other hand, we used very simple surrogate time series, and improving these surrogates might change the result somewhat. So, there might be ways to tune the convergent cross-mapping so that it performs better. And then the weighted lasso approach had comparable performance to pairwise Granger causality testing. So, the true model interaction or the interaction that we put in or equivalent to conditional Granger causality. So I was quite surprised that pairwise Granger causality did as well. So we asked a little bit why that is. So one reason might be that the weighted lasso could have a better performance if we allow to increase the number of maximum time lags above 1. But because the nice package by Camille Charbonnier and Julien Chiquet was restricted to MAR1 modeling, we stuck to that. And also we had good indication computing BIC that this lag was 1 or 2 for in our case. But in other cases, there might be a need to add more time lags. So how to do that? So it's probably possible to do a joint selection of both the maximum number of time lags and the interaction matrices with BIC. And another approach, which I think is a little more tricky, is to select both the number of time lags and the structure of the matrices, the interaction matrices, using the group lasso. And there are people in econometrics who do that. The problem is that there are many ways to specify the group lasso to do this sort of penalization. So they have an R package which is called Big var, and I haven't managed to make it work properly, but some people in ecology, Menali and co-authors did. So this is an interesting way forward. Now, you can note that because of the results that we had, we have so far avoided to model strongly autocorrelated environmental forcing and many species dynamics together. We try to keep this source of complexity separated. But of course, in real life, this is a common situation. So I work on phytoplanktonic species that react quite similarly to temperature, although there are slight differences in how they react. So this, I think, would be an interesting avenue for model development. Although, as we showed, in absence of additional constraint, if there's a strong nonlinearity in the underlying data generating mechanism, that's probably going to be very difficult. So far, everything I have mentioned to fit large multivariate autoregressive models relies on the sparsity assumption. And I've listened to the talk of Benjamin Poignard, which was just before me in this seminar. And another idea, of course, is to abandon the sparsity assumption, to do something else. So some people have tried that in ecology. They call this the community level drivers method, but really it's econometricians would say it's a factor model method. And it's by Ovaskainen and co-authors. They're mostly coming from Finland and Norway. And they published this paper in a biology journal, but most of them are theoreticians and statisticians, and they do really interesting stuff. And for this paper, they also teamed up with David Dunson, whom you may know from his work in Bayesian statistics. And so what they did was to analyze data for about 100 species, so microbial data. So microbial data have all sorts of problems due to the fact that they're on a simplex, but let's not talk about these complexities here. What they did was to model the interaction matrix by assuming that's what you see pictured here, that there's a low rank representation with the so-called factor loadings. And that's why you have these blue and red colors here that structure this matrix. So they've analyzed real data, and they also simulated data sets. And they simulated 4 models. They simulated a model without any interspecific interaction, a model where the matrix is absolutely full, a matrix in which you have sparse interactions, and a matrix which has a low rank representation. So I won't go into all the details in this slide, but basically they have shown that for the data generating model with sparse interaction, you can recover that model and find that it's the best model. And for the model with the community level drivers, with the low rank representation, at least on simulated data, you can also say that, you know, this is the best model. So if we assume that what they've proven with simulation is approximately okay to be applied in real life, then they have identified that their data set was better represented by community level drivers. So a low rank representation of the matrix. Personally, when I look at this kind of matrix, so I think this is a really nice modeling exercise, but I tend to be a little skeptical that we can have these type of matrices in ecological data, because quite often you have a strongly modular structure of ecological networks. Sometimes you have some nestedness too, but modularity is usually a common feature. So I would tend to think that irrespective of the fact that we keep the sparsity assumption or not, it would be a good thing for, you know, methods inferring large networks, that they're able to deal with the modular aspect that we find in most ecological interaction networks. So I will try to close on this. The paper has been published in Theoretical Ecology. You can find a reprint at arXiv, and there's all the code that is available too. And just to follow up a little bit on what I'm sort of things that interest me at the moment. So I'm really interested to decipher how do the links we infer could depend on links that we assume. So let's say that I know that I have two species that are strongly affected by temperature, and I have a strong prior on the temperature effect on the model. How will that constrain my inference about the interaction between the species? Like, can I get away with it by adding prior knowledge to the model? So I'm interested in this, and also in identifiability issues in these models. So even when you consider the nonlinear data generating model, it might be that even if you were fitting exactly the true model, you may not be able to recover the parameters of the true model. So this is something I'm looking at with formal identifiability techniques, and also techniques to mix different data streams. And I have a postdoc position that's opening on that, if you know anybody that may be interested. So I'll stop on this, and I will thank Paul for inviting me.
Thank you very much. So it was very interesting. And may I just ask a question about these low rank assumptions? I was thinking we used this idea in a paper with Pierre Alquier and Rémi Garnier and Karine Bertin, which appeared last year. And I didn't know that other people were also working with low ranks. And so that we used it for, it was coming from a question of online retail. You know it from since you are in Bordeaux, and Cdiscount is working with that, and we have a PhD student. So Rémi Garnier is a PhD student working there, and so we were not neither very convinced with the numerical results we obtained. In fact, it was, but maybe there are some. It would be interesting to compare with the paper of those northern people. Thank you. So thank you very much for all your for your talk. I don't know, are there other questions and comments?
Yes, I have a question about. In fact, I am a bit confused about how to measure this abundance data. in the sense that so here you use a multivariate autoregressive model, which is more or less a linear model after the log transformation.
Yes.
And for instance, in the literature, we find many other tentatives to model the data. Sometimes they consider this as a count data, and then they use a kind of GLM models with, for instance, some distribution like the Poisson log normal distribution. So it is also possible to measure causality in a nonlinear model using a GLM model, so generalized linear model. So what is the best approach, and the most relevant method to take the logarithm of the data, or can we work with other type of model?
Yes, so that's a good question, and that's a question that ecologists have been fighting over. So if you look at the literature, there's a journal in which many people publish like methods-oriented articles for ecology. It's called Methods in Ecology and Evolution, and there's been I think at least 5 papers answering to each other whether we should log transform count data or not. You know, irrespective of these autoregressive models, because the question is also true in the context of regression, like multiple regression, simple multiple regression. So personally, I'm a pragmatic person. You know, I think that if the counts are really big, you can log transform. If the counts are really small, you cannot log transform. And of course, it's a trade-off, you know, because if you have a few small counts in a data set in which most of the counts are really large, then there are various ways to choose what to do. You know, then this is what people call degrees of freedom of the analyst. You know, there's no one single technique that will work uniformly best every time. But some people who looked at this more precisely said that it was critical to use GLMs, for instance, when you had a mean value of the counts that was approximately 1. But for this to happen, you need really small counts.
Yeah, you need some zeros, actually.
Yes, and there's been some of the controversy in ecology is also due to the fact that there's been a paper proving that you couldn't log transform count data, but when evaluating the comparison to log transform data, the authors had a confusion between means and medians. And so their whole comparison was, you know, biased. So there's a lot of controversy about it, but I think that most of the time, so long as the counts are really big, or even, you know, like if you have 51, 27, 103, you don't really care that these are counts. If you want to explain, if you want to predict, of course, if you want to predict a precise value, then it may be a good idea to have a GLM, because then you fit the exact distribution that you want to predict. But if you want to explain and infer coefficients values, you may not need to do all that.
Yes, I understand, because if we transform the data, for instance, if you want to make predictions, and if you transform first the data, you obtain the best prediction, and then you take the inverse of the transform, so it is not equal to the best prediction. So yeah, it's better to work with the initial scale, I think. Okay.
Yeah.
Okay. Sorry. Thank you.
Okay, so I don't know. Maybe we should just stop recording, and we can discuss a bit more. What about?
Yes.
Right?